PhD candidate in the Department of Physics, and I'm going to be talking about a volcano in southwestern BC called Mount Meager. And I've set myself the ambitious goal of trying to answer 6 questions for you in 5 minutes. They are: what is geophysics? What are radio waves? What is magnetotellurics? Where is Mount Meager? What is geophysical inversion? And then finally, what is the resistivity beneath the volcano? And if you don't know what some of those words are, hopefully you will in 5 minutes. So how can we look inside the Earth other than by digging holes or drilling holes? Well, we can use physics and technology, and this is what geophysics is. So if we understand the physics going on underground, then we can use math to interpret measurements taken at the Earth's surface. For example, if we know that different rocks have different densities, we can use gravity to kind of paint a picture of what's going on underground. If we know how sound waves propagate through different types of rocks, we can use seismic to image the subsurface. And if we know how electromagnetic waves, such as radio waves, interact with different types of rocks, we can use them to paint a picture of the underground. So what are radio waves? They're low frequency electromagnetic waves. You're probably familiar with microwaves and visible light and whatnot. So radio waves come in lots of different frequencies. The Wi-Fi router that you use at home probably uses 2.4 gigahertz or 5 gigahertz. Your FM radio is slightly lower frequency. AM radios are even lower frequency. Magnetotellurics, which is the geophysical method I use, uses even lower than that and even beyond any human-used radio waves. So very, very low frequency. And so what is magnetotellurics? MT, which is what we call it for short, uses or measures electric and magnetic fields at the surface of the Earth. And these measurements tell us about the electrical conductivity of the Earth underground. And so this is just how well electricity can move through the Earth. And I will be talking about resistivity, which is just the opposite of conductivity. Where is Mount Meager? It's a volcano in southwestern BC, just to the northwest of Pemberton and Whistler, up here. And so this next question is, what is geophysical inversion, which you probably haven't heard of. But to turn geophysical data into an actual model that we can look at, we use something called geophysical inversion. And the first step in doing this is to take your study area. Here's my study area around Mount Meager. And you chop this area into little bricks, basically like you're trying to make a model out of Lego blocks. So it'll look something like this. And so what I did is I took my study area and I cut it into more than 2 million blocks. And that's the starting point for making my geophysical model. So if we were lucky enough to be able to kind of see into the Earth magically and know exactly what was down there, we could combine that with our knowledge of physics, and it would tell us what data we would expect to find, for example, at each of these red dots. Obviously, we can't do that. So what I do is I go out into the field and I measure data. I went and measured data at each of these red dots, or most of them. Some data I got from other people. So if you have measured data, you can combine that with physics, and that will give you a model of the Earth. And so this process shown down here is geophysical inversion, and that's what I use to create my models. So let's take a look at my model. What is the resistivity beneath Mount Meager? Near the surface, there is low resistivity, and remember that just means high conductivity, near Mount Meager and the volcanic vents. And this is due to hydrothermally altered rocks and salt water. And so this is associated with the geothermal system, which can provide energy in this region. If we go down deeper, this is now about 8 or 9 kilometers beneath the surface. There's a very large conductor. And so this is more likely because of melted rocks and possibly also salt water. So salt water, melted rocks, and other geothermal fluids have low resistivity. If we look at some cross sections from west to east, we see that deep magma body, that deep conductor, and then there's regions of elevated conductivity reaching up towards the surface in several areas, and these are likely related to hydrothermal systems. So these near-surface hydrothermal systems can provide energy in the form of geothermal energy, and so I'm studying the bigger picture, kind of the deeper structure to help the team of scientists that are studying this volcano for geothermal resource potential. I would like to thank my PhD supervisor, Dr. Martyn Unsworth, and I would also like to thank everyone that provided funding and other resources, FES, NRCan, Geoscience BC, and Compute Canada. We can chat during the discussion at the end. You can also contact me via email, Twitter, and LinkedIn. And hopefully that was 5 minutes.